Start with something you know, a parabola. You have seen it 1,000 times, but stay with me because this one is hiding something remarkable. Its equation is x squared equals 4ay. Simple enough. Now here's the trick. A single number t can describe every point on this curve. Set x to 2at, y to at squared, and as t varies, the point traces the entire parabola, one parameter, the whole shape. And you can check this yourself. Plug 2at and at squared back into x squared equals 4ay. Both sides give you 4a squared t squared. It works perfectly. Now fix a point on the curve. At this point, the parabola has a tangent and its slope turns out to be just t. The tangent equation tx minus y equals a t squared. Clean. Perpendicular to the tangent is something more interesting. The normal. Its slope is minus 1 over t. And the normal equation is x plus ty equals 2at plus at cubed. Remember this line. It is the one that matters. Now here's where things get curious. Pick a point Q, somewhere above the parabola. From Q, how many normals can you draw back down to the curve? It comes down to the cubic. When you substitute Q's coordinates into the normal equation, you get a cubic in T. And here is something most people forget. A cubic, just like a quadratic, has a discriminant. When that discriminant is positive, 3 real roots, 3 real normals. When it vanishes, you are on the boundary. That boundary traces this beautiful cusp-shaped curve, the evolute, and everything inside the cusp is the 3 normal region. So let's pick a point Q inside. 1 normal, a second, and a third. Each one reaches the parabola and touches it at a foot. Now connect those 3 feet, they form a triangle, and draw the medians, each line from a vertex to the midpoint of the opposite side. The 3 medians meet, as they always do, at the centroid. But look where it lands, right on the axis, exactly on the axis of the parabola. That is not a coincidence. Let's test it. Keep Q at the same height and slide it left and right. Watch the feet rearrange, the triangle flexes and shifts. But the centroid, it does not budge, not even a little. Now let Q wander freely, anywhere inside the 3 normal region. Keep your eye on the centroid. It slides along the axis, only the axis. It will not leave it, no matter where Q goes. So, the 3 feet P of Ti sit on the parabola. Their coordinates are 2ATI and ATI squared. The x-coordinate of the centroid is 2a over 3 times the sum T1 plus T2 plus T3. And this is the heart of it. Look at the cubic again. A t cubed plus 2a minus k times t minus h equals 0. There is no t squared term. And when a cubic has no t squared coefficient, Vieta's formula is immediate. The sum of the 3 roots is 0. So gx, the centroid's horizontal coordinate, is 0. The centroid sits on the axis, always, regardless of where Q is. But that is only half the story. The y-coordinate of the centroid is a over 3 times the sum of the squares of the 3 roots. Expand that sum of squares. It equals the square of the sum, which we just showed is 0, minus twice the sum of pairwise products. And Vieta tells us those pairwise products sum to 2a minus k over a. The a cancels, and what remains is beautifully simple. 2 times k minus 2a divided by 3. And notice, h is nowhere in this formula. The centroid depends only on k, only on the height of Q. And that is exactly why the horizontal sweep worked. When Q slid left and right at fixed height, h changed. But the centroid could not care less, because it only ever depended on k.